Welcome to week 3, day 5, Friday, week 3. And we're going to learn more about rendering today. I know last time I think it was Biddinghoven was like, do we really need to know this stuff? And it's just like, yeah, if you're using Unreal Engine, like it'll kind of do it for you, you know? But at the same time, like, you kind of got to know what's actually happening underneath the hood. And especially if you want to be somebody like Logan who wants to actually work on game engines, then this is a weird angle. Here. And these things kind of come up a lot in a lot of different contexts. So we're going to talk today about barycentric coordinates, and we're going to talk about rasterizing a triangle. So last time we did line rendering, and if we wanted, we could probably render an outline of a triangle pretty easily, right? Like, what was it? Vim main.cc. That's our lines segment thing here. Okay, so we could, rather than reading in a point or something, we could just make a triangle. So we could just do like line 1, line 2, line 3, and this one might go from 0, 0 to what are we gonna do, like a right triangle or something, to like 10, 0, and then this one might be from 0. This one might be from 10, 0 to 0, 10, and this one might be from 0, 10 to 0, 0. So if we compile this, didn't like it. Yeah, maybe I should have an extra close parentheses there. Okay, so if you compile that, run it. Let's render all 3 of the lines, maybe. There we go. Line 2, line 3, and oh, it's clearing the screen every time. Yeah, let's do that. Let's pull you out. So this is actually a pretty common approach, right? You blank the screen, and then you rasterize things onto it, then you display it. Typically, you'll do something called double buffering in situations like this, where you've got one screen buffer that's being output to the monitor, and you're working on another one. So you start off by blanking it, you're setting it all to black or whatever, and then you rasterize all your triangles on it, and then once you're done, you swap the buffers. And so you'll have a pointer to a 2D array of screen colors. And you'll have another one, you'll have one for the first buffer, one for the second buffer, and when you're done, you just swap the 2 values, and then the monitor will, and then you pass it to the monitor, and they swap back and forth. So you're constantly drawing not directly to the screen, but to an off-screen buffer, and then once you're done, you swap them. You can actually do that using a terminal, which was kind of news to me. Like, terminals actually support off-screen rendering. So rather than you visually seeing this thing draw on the screen, if it was really slow, you would actually see all the pixels appear one at a time. Rather than that, you can actually render to an off-screen buffer and then tell PuTTY to swap. And you can swap back and forth between the 2 different buffers, and then it will just all appear at once. We're not going to do that. So we are just going to clear the screen and drop live. Did I screw that up? What the heck happened here? Two of them worked, but might have a bug in the slopes that go that way. Let's just verify that real fast. Yeah. So the slope is maybe backwards. So vertical line. Oh, it's because they're absolute valued. That's why. Yeah. That's why. Okay. So we only get positive slopes. We never get a negative slope because of that. All right. So it's not abs it here. Instead, we are going to abs it here. And maybe. Come on, will you? So we're getting one. We're getting one line now. What the hell is happening? Right.
Line drawing is hard.
There must have been a bug from yesterday that we didn't account for. So, 10. So we're only going to draw line 1, vertical line here. Is it row column? Yeah. Okay. So let's change this to a horizontal line. Okay. All right. Let's change it to a diagonal line. Okay. Let's change it to a backwards diagonal line. So we'll start at row 10, column 0, and go up to 0, 10. Let's see if we can do that. Okay. All right. So all three of these are working. So are they just overwriting each other, maybe? And rasterizing them? So, Muya, remember how we were talking about line rasterization algorithms last semester? So I got a pretty decent one. It doesn't do anti-aliasing, and it could be fun to talk about anti-aliasing. But this one at least will give you a exactly 1 pixel thick line, no matter kind of what the slope is. So why are you not? Let's just not even put them next to each other and see if we can figure out why they're. Let's draw 3 of these, line segment. It's just not drawing these. What's going on here? That one's not drawing at all. Why are you not drawing at all? Might be off the edge of the screen, maybe? Okay. That drew. That drew. Ooh, that's not drawing. Okay. So that's a problem. So if we pass in 10, 20 to 2010, it doesn't draw. Well, if we pass it in the other way, it does draw. And that shouldn't even be a thing because oh, it's because of the negative maybe here. If that's a negative, then I think we assume these things would have to be positive. Yeah, that's why. So we need an abs there too. Okay. Debugging, fun times. And there we go. Okay. because I pulled the absolute value off of these, and so the code down here assumed they were positive, and so these for loops wouldn't work with a negative number. So that should be that. I've said twice now, so let's just verify that this will draw. And there we go. So we got that. All right. So let's put it back the way it was before. 0, 0 to 10, 0, and 0, 0 to 0, 10. Nope, that's history. There. So there is a triangle. Okay. And rather than what we have now, let's talk about colors. Okay. So when you colorize a triangle, like we're not even getting to like materials or any of that stuff. We're talking about like the 1980s. There's a couple different ways you can colorize a triangle. So let's zoom in on this a little bit. So let's say you've got, these are quads, or maybe they're two triangles back to back, it doesn't matter. And so here with flat shading, what you'll see is that the whole triangle gets the color of like one of the vertices, right? So like maybe the top left or the first, it doesn't really matter. The entire quad gets shaded based on the normal of, actually no, I take it back. They all have the same normal, so they'd all be shaded the same way. So it looks like that. With garage shading, what happens is that the normal essentially is sort of changes based on the 3 different points on the triangle, because the 3 different points will have different reflections of the light coming off them. And there's garage shading, which is faster than Phong shading. Phong shading looks better. With garage shading, you can still see the sharpness of the thing. With Phong shading, it actually looks pretty good. And so we're gonna not even go here necessarily yet. What I want to do is actually just talk about colors. And so what if you have a triangle that has a red corner, a green corner, and a blue corner? Then you have to interpolate between them smoothly, right? C++20 has a lerp node, so, or lerp function. Shouldn't call it a node, it's not Unreal. But we are going to need to change these just to floats here. We're going to need to change this into a point class, because a point is going to have a color. Oh, we already have one. Cool. We're going to need to add a color to it. So we're going to do a unsigned char 8, unsigned int, sorry, unsigned int, which is like a char. T, it's an unsigned 8-bit char, RGB, like that. And so now every point is going to have a color associated with it. And I'll initialize these to 0, I guess. Just it makes me very nervous to have uninitialized variables and things. I don't even have a constructor, so we'll make one. So one of the problems is that these line segments have all the points duplicated twice, right? What we really want is not having to hold every point twice. We want to hold every point once. So maybe we could make a triangle class, or you can do what's very common. You just have an array of all the different points, and then the line segment can be an index into those arrays. Which one would you like to see? Would you like to see kind of the vertex buffer method, so you don't have to duplicate all of your vertices? These are the points are vertices. You guys kind of want to see a vertex buffer when we do a triangle. Okay, so let's do a vertex buffer. So globals aren't the best, but whatever. We'll make a vector of points called vertex buffer. And so this is just going to be a collection of all points in our models or whatever, right? And then you don't have to keep duplicating the points over and over again, right? So the line segment would just be an index into the vertex buffer saying vertex 1700 is my start point, vertex 2500 is my end point. Do you guys understand? Then you don't have to, like, especially when you have a mesh that's connected really heavily, you don't want to have to keep holding all that redundant information. Just an index is good enough. So we are not going to do you anymore. Instead, we are going to have a size t called start index and end index, like that. Holds the starting and holds the index in the buffer to our start and end points. So when we rasterize now, we have to. This won't compile, right? Because we no longer have our own copy of the point data. So we're gonna have to pull it out. So that's pretty easy. We just say point end is equal to vertex buffer dot at end index. And point start is equal to vertex buffer dot at start index. And obviously you wouldn't be using dot at right in 3D graphics code. That's noticeably slower, but I always start safe and slow. That's my approach. So we'll just start with these set equal to 0 as well, just for the hell of it. Okay. So with that change, did you guys see the change there? So rather than holding our own and each line segment having a copy of the start and the end, and it would have to have its own copy of the RG and B values. And if they ever get mixed up, then the ending point of one node might have a different color than the starting point of the same point, right? Because you got multiple copies of it. Nah, forget about it. So, yeah. So all we have is one copy of all these things, and then the line segments will hook them up. Okay. Then after that, the rest is the same. And then for the color, we're going to set the background color to be... that's a good question. That's a good question. We'll start off with it just being the start. The start colors. So start dot red, start dot green, and start dot blue. And we should probably initialize these things to white, huh? Just to so that it'll appear on the screen, right? Okay. So okay, so that is Muya still here? Yeah. So Muya, the approach I took for the rasterization this semester versus what we did last semester was just to see which way the line is longer. Is it longer horizontally or is it longer vertically? If it's longer horizontally, then we loop from the left to the right, drawing out each point and just moving up and down based on the slope. So we get exactly one point in every column, and it'll go up or whatever. And you'll never have any breaks in the line because the steepest angle you can have is 45 degrees. And 45 degrees is still every pixel's touching each other. Once you go steeper than that, remember the problem we had last semester with the points not connected all the way? Then the other if statement takes over, and we loop up the line or down the line, depending on your perspective, and we go one pixel at a time that way. And again, they're all going to be connected because at most it can have a 45-degree angle, so all the pixels are going to be connected to each other, and you'll get exactly one pixel per row as you go up. So pretty easy. And we were drawing random colors on it, but we're not anymore. We're not going to do random colors. We are going to do something totally different now. We're gonna show you guys how to colorize. Good. So maybe we'll do this. Nah, it's gonna hard code it. So I'm gonna say point 1. Yeah, fine. Nah. Just gonna do it directly. Dot in place back. And so we're gonna write in all the arguments to the point, which is gonna be row, column. Is it row first? Row first, yeah. Row, column, then RGB. So rather than making it temporary, we're just going to do it all at once. So it's going to be row, column, RGB, like that. Okay, so let's say the row is going to be 0, column is 0, red is going to be 255, green and blue are zeros. So this is going to create a new point in the vertex buffer that's at the top left corner of the screen that is perfectly red. And we need a semicolon on that. And we'll just add a couple more vertices here. We're going to recreate our previous thing. So we're going to have 10, 0. And this bad boy is going to be red, green. And the next one, of course, is going to be blue for maximum primary colorness. Okay, so now what we have is we've got our vertex buffer with all of our rows or positions and our colors, and in a real vertex buffer will maybe even have more information than that, but that's good enough for now. And so for our first line segment, we are going to just tell it the index of the vertices that we care about. And if you look at like 3D model data, it usually starts off with like a vertex, all the vertices, and then the triangles are actually just the indices into the vertices. So that's how it constructs meshes. And if you have a mesh where the triangles are sharing points, then it'll be held as like a tri-strip or something like that, or a fan, so that you don't even have to repeat like if two triangles share edges, they don't have to repeat 2 of the points either. So claim D server crashed 5 times. Cool. Index 0, index 1, index 0 to index 2, and index 0 to index 1 to index 2. Okay, you guys understand this? I wonder if I can open up like a 3DS file or an MDL file or something like that. I wonder if these are actually in ASCII readable format. Vim save us. No, it's in binary. No. Yeah, but I've edited 3D models in text editors before. I wrote a macro actually. We had a model where all the triangles were backwards, and so I wrote a macro, not a program, a macro that would flip the triangles around so that they would be facing towards us instead of away from us. That was fun. Okay. All right, so let's try this. Let's see how this goes here. And there we go. So we got red, and we got green. And the reason for that is because the first one is here. So let's do 1, 2, 2, 1, and 2, 0. So everybody gets their time to shine in the sun. 0, 1, and 2. Okay. RGB. Why are you not drawn as blue? Shit. Oh, it's because it swapped them. That's right. It swaps them so the leftmost one gets drawn first. It's fine. Actually, it's not fine. It's going to mess up the colors. Damn. Ah. Yeah. Damn it. You can't just swap them anymore. I don't want to mess with it right now. just leave it be for now. Okay. Have fun with your barycentric coordinates and vertex buffers. Yeah, we didn't do vertex buffers last time, Leah, but yeah. Did we? I don't know if we did. We did do barycentric coordinates. Okay.
Kind of. I'm learning more of it in OpenGL anyway.
Yeah. All right, cool. Are you taking off, Leah?
Yeah, unless there's anything you want me to talk about.
I don't know. What do you want to talk about?
Well, I mean, I don't know if it's still in there, but if you talk about the barycentric coordinate stuff, I do still have that, that triangle rasterization assignment with the intersections and the, all that stuff. I hope I backed all that up.
Look at those lines. Look at those lines, Maria.
That's what I'm trying. Yeah, you gotta do rasterization. That's the real one. A projection, no. I remember that was a complicated mess.
Which one are we talking
Rasterization.
About? Rasterization.
That was the pretty one.
Oh right, yeah. So it does Z buffering. Yeah, it's cool. I like it. And so, yeah. Is that not working? Crash.
I didn't type the word barycentric anyway.
Are you doing the math? Yeah, cross product.
Yeah, I had to calculate a plane equation to figure out the it's the rasterize function. It's the where is it?
Yeah, cross products.
Yeah, it's calculate red area. That's where it was.
Yes, the barycentric coordinates are just the cross product, right?
So, yeah. So, I mean, it's just finding out how far you are from the center, or how far you are from each corner.
Right. Yeah. And so if you cross product this vector with this vector, right?
Huh?
Then I think if you cross product it with each, that's what gives you the barycentric coordinates. Something like that. Yep. Or it's the fraction you are, yeah. Or you can dot product it and see what fraction you are, or something like that. Let's see.
It's all in my code.
It's the relative area of the triangle, right?
Yeah, so you connect a given point to the edges and then see how large each of the areas are that are created.
If you dot product, if you dot product it, dot product gives you the area of the rectangle, right? Yeah. Right? Yeah.
No, I think it's magnitude of your cross product divided by 2.
Yeah, if you want a triangle, right? But the cross product itself, if you don't divide it by 2, that's the area of the rectangle formed by the two vectors. And for the barycentric coordinates, it's the relative ratio. So I don't think you actually have to divide by 2 if you don't want to. Because
it can't be the dot product, because then the farther the
it's not dot product, it's cross product.
Okay, cross product.
Yeah. Because you cross product this vector and this vector, and so when it gets down to completely parallel, it's 0, right? And if it's completely at 90 degrees, then you end up with a right triangle, 1/2 base times height, right? And so, my point is, like, you don't actually technically, I don't think, have to divide by 2 to get the actual area, because all 3 of them are going to be divided by 2. And so if you're just computing a ratio, like, you could just take the cross products.
Yeah, you don't actually have to divide at all. Yeah, it's just a ratio.
And so it's the relative magnitude of the cross product of the 3 is the barycentric coordinate. So to the 2 students who don't know what we're talking about, let's talk about what we're talking about. And well, you can take off if you want to, or you can hang out. It's up to you.
I'll see you later.
Okay, see you,
dude. Bye-bye.
So when you want to colorize a triangle, and it's really easy if the 3 are the same color, right? It's just red or whatever. But let's say you've got one that's red, one that's blue, one that's green. Then you want to smoothly shade from one to the other. On the line, it's pretty easy. It's just a lerp, right? And right now, I'm just drawing everything as red. You know, whatever the starting point is, I just draw as red. But that's why I said I'll come back to that later. It should be a lerp, and I really shouldn't be swapping the two pixels because it's going to mess up the colors on the screen. But I don't want to mess with that right now. So for the line, it's pretty easy. You just lerp it between the color of A and the color of B, or I guess C here. And that'll colorize the line nicely. If you lerp between A and B, it'll smoothly transition from red to green. Nice. Lerp from blue to green, it'll be nice. But when you're colorizing the center of a triangle, then it gets a little tricky. And it gets tricky because you have to figure out how far away you are from blue, green, and red. The closer you are to blue, the more blue it is. The further away you are from blue, the less blue it is, right? So up here it's 100% blue, down here it's 0% blue. And so what you do is you take the cross product of A to C and A to X. X is the point in here, right? And you figure out the relative ratio, like you might have seen this thing creating a triangle here. You figure out the relative ratio of the triangle created here and here and here. And if you're red, the bigger this triangle is, not the ones near you, not the two that are near you, the one opposite you, right? Because if P is really close to B, then it's going to be really red, right? And so the color you get is going to be the fraction that beta is versus the total. And then the fraction, I guess, let's see, C is going to be teal in this one. So the amount of teal that it gets is based on the fraction of gamma versus the total. And the fraction of yellow it gets for A is going to be the fraction of A versus the total. You do that at every point. And then you've got a nice, smoothly shaded, triangle like this. It looks really nice, like you saw when we did it last year for this class. I don't know if I'm gonna have you guys do it. Maybe not. All right. I kind of want you guys focusing on the projects more. So yeah. So AY minus CY. This is going to be AY minus CY. So that's creating this vector here times X. X is X coordinate. Yeah, okay. That times Y coordinate, XC, X minus AX. The Y coordinate. Yeah, so basically it's basically you do a bunch of cross products. And so like right here, it's going to create 3 triangles that are equal in size. And so it's going to be 1/3 red, 1/3 blue, 1/3 green. Because the green triangle, which is this part here, is the same size as the red triangle, same size as the blue triangle. Whereas when you start getting closer to red, then you get this triangle for, you get this triangle for red, which is bigger. And the triangles for blue is smaller, the triangle for green is smaller. So, okay. So let's maybe implement some of that stuff for you guys. Let's see what we can do here. So vim main.cc. I'm still kind of annoyed by that swap not being the beautiful solution I thought it was. Well, it was for yesterday. Now it's going to screw up our colors. No. Okay. So the first thing we should do is just lerp. So we should lerp the colors from the starting color to the ending color, right? So I'll just pull this out into a separate variable instead of doing it all in one take. So unsigned integer 8 underscore t. Red is going to be equal, so it's going to be a lerp. Lerp is C++ 20. Might be C++ 20. So we're going to lerp between the starting red color and the ending red color, and the fraction that we are from the start to the end is the alpha, and that is going to be I divided by horizontal distance, and I might want to make this a float or something. Double I divided by horizontal distance. So it'll smoothly transition. The red doesn't like that because lerp doesn't exist probably because we're not in C++20 mode. Dash std equals C++20. Lerp is not declared. All right. It's bizarre that this was not added earlier. It's not like you couldn't write the function. It's in C math. Okay. It's odd because I don't think it's actually in the C library. You know. There you go. So. I don't think C actually has. Does it? I don't know. I'd have to look that up. Okay, so we got here red. We got here green and blue. Are you guys following with what I'm doing? It's okay. You can say no. It's not like I'm grading on this or anything. Like if you don't get what I'm doing. Just ask. The starting point has an RGB value. You're not sure what lerp is. Great. So the starting point has an RGB value, right? Like it might be red, 25500, and the ending node might have it will have an RGB value, but it might be blue, 00255. And so what you want is as the line goes along, you want it to smoothly transition from red to blue. And so lerp stands for linear interpolate. And it's a fairly easy equation where basically you have a starting value, an ending value, and this is a number from 0 to 1 that is what percentage of the starting value it is. At 0, it's all this value. At 1, it's all that value. And then it just does algebra. It's alpha, 1 minus alpha times this plus alpha times this. So when alpha is 1, it's all that. When alpha is 0, it's all that. And then it's just a simple function to interpolate between the two. And so if we do this, and we'll do it again, y for y, do this again down here, then it should look nice. Ooh, it's all black on the vertical side though. Because we're not doing horizontal distance, we're doing vertical distance. 5s vert. There we go. And so look, we got a nice little transition. Of course, the blue and the red are switched because I did the swap thing. All right, fine. I guess I'll fix that. All right, so if starting column is less than the ending column, so we've copied these values out. So we just want to swap the column. Really, we don't have to swap the entire value, huh? Are we using a row at all? Starting row, I guess so. Okay. I'm going to keep what I had last time, so we're just going to switch the columns, because these are not the original vertices anymore, right? We copied it out of the vertex buffer, so we're actually messing with a copy here. So we got row and row. And so the columns are going to switch, the rows are going to switch, but the colors will stay the same. And for y, so I can keep my hack here. And now the colors work. Hot dog. All right. So we've now got a wireframe triangle, essentially. And we could even make a triangle class, and each triangle could be a set of line segments, or even better, it could be just the indices into the vertex buffer. You guys want to see that, like a little triangle class? Or we probably should make a triangle class, huh? Yeah, because we're going to need that anyway. So we're going to do barycentric coordinates. All right, so we've got line rasterization, and I'm just going to call this guy just line segment, because we never implemented this one. So it's just lines. It's the official. This one someday. All right. Okay, so we got line segment. Now we are going to do the triangle class. And so the triangle class is going to have what? What is going to define a triangle? What do you guys think? Three points. Okay. Am I going to actually have a point? You want point A, B, C like that? Nope. We want indices in the vertex buffer. Because we don't want to have each triangle have its own copy of the points. The reason is if you have triangles that are sharing edges, then you don't want one triangle's A point and another triangle's A point to be the same, and then one of them turns red and the other one doesn't turn red because they're the same point, right? So we have them indexing into the vertex buffer. Yep. So we've just got indices here, and we got A, B, and C are the things, and then we need to make a raster function. And yeah, okay, so rather than this, clear screen we can keep. And at the end, we should probably reset our colors, just because you don't end up with random colors kind of screwing up your screen that way. Okay, so we're going to have a couple points here, and now we're going to make a triangle. Okay. So we're going to make a triangle, and the triangle is going to just be points 0, 1, and 2. Let's give it a name. Try one. Triangle, or just try one. Whatever, we might do more. Okay, so triangle 1 is going to have 3 points inside of it, and remember these things are indices into the vertex buffer. So we don't, we just have one set of canonical list of all the different vertices in the world, and then we can link them up in different ways. And yeah, so let's do a raster on it. Can we cheat at this? Can we cheat at this? I think we can cheat at this. All right. All right. I think we can do this. All right. So line segment AB, line segment BC, and line segment AB, AC. Line segment first line, second line, and third line. And then we will call maybe we don't even need to name them. Let's do this. Let's do this then. There you go. So we don't even have to make a variable. This is a anonymous variable here. So it's making a variable. It's calling the constructor, but it's not actually giving it a name. And that's fine, because it exists for a brief moment in time, like a mayfly, and it draws its line, and then it goes away, never to be seen again. So have you guys seen this before in C++? Where you can make variables, like I'm constructing a variable with no name, there's no name on the variable, and calling a function on it, and then that's it. It goes away. You can't hear me. Oh. Hello? Hello? Let me check my sound settings. Recording, microphone. Hello, hello. Hello, hello, hello. Turn it up, maybe. Hello, hello, hello. Okay, it was your end. Okay, never mind. Sorry. My stupid Yeti microphone. If you wiggle the USB adapter on it, it turns off. And so it's just got like a badly soldered USB port on it, and so occasionally, like, you know, I'll move it and then the thing turns off, and when it turns off, then like the recording software is like, there's another microphone attached, like on the webcam, or I've got my Rocksmith USB cable, and it switches the audio input to that, and then it's recording off my electric guitar and not my voice. That's some good USB Type B. Yeah, it's a micro USB connection, and it's really it's not well made, even though it's Yeti, which is supposed to be a good company. If you bend the microphone forward, what happens is the USB port contacts the back of the stand. It'll rotate pretty far, but then the USB port hits the back of the stand and it bends it, and that's what I think probably snapped the solder on it or something. It's just, I don't know, poor design maybe, or it's my fault. I don't know, one or the other. But yeah, it does cut out occasionally. So. Okay, so yeah, have you guys seen this before? Where this is making a variable of type line segment, constructing it with I don't know, these two numbers here, and then it's calling a function on it, but we're never giving it a name. We're not giving it a name because it simply doesn't matter for now. We're gonna probably give it a name, but this is funnier for now. Okay, so if we do this. Ooh, it doesn't draw anything. All right, cool. So maybe we will give it. Maybe we will give it a name first. Second. And third. These are line segments. Yeah, you can make functions with no names. They're called lambdas. You make classes with no names. You can do that if you want. No object oriented. It's a no object oriented. Yeah, very, very funny. A B B C A C. Okay, and then we're gonna call first dot raster, and we'll call second dot raster, and third dot raster, and see what we get. Nothing. Okay. Maybe if I called the raster function, that that might help. There we go. All right. There we go. All right. So yeah, maybe if you call the function, it'll work better. Oh, well, it's fine. I wanted these things to exist anyway. So some job security tips. Yeah. It's you know. And the funny thing is, like, a lot of people think that's good coding, right? Like lambdas are, and I'm not even using that sarcastically. Like, you know, lambdas are considered to be good coding practices. But if you encounter C++ people from the 80s, they have no idea what they are, right? Like, there's so many people that studied C++ prior to C++ 11, prior to 2011, and things like range-based for loops even they've never seen before. Lambdas, like, you know, lerping, obviously. Now, they probably know lerping. They probably had their own function for lerping. Yeah, and so there's a lot of stuff that you can add that will give you job security. Okay, so there we go. So we got a triangle, and it's rasterizing the triangle. Now we need to fill the triangle. Okay, so we're gonna go through. We should probably keep track of our min and max. Like, let's make an A, B, B or something like that. Should we? Yeah. Okay. Int min row is equal. Oh man, I don't want to do this. We'll have to make an ABB class. We got 10 minutes left. Now let's just go for it. Let's just be inefficient. It's fine. So we're gonna go through every point on the screen and see if it's inside the triangle. Okay. So for do I have a global or something? I don't, do I? So we'll just get the terminal size. Okay. Okay, so we're going to get the number of rows and number of columns. Okay, so for every, we wanted to go left to right and top to bottom, because that's how terminals work. So we want to start at the leftmost column, go to the right. No, we want to stop at the top row, and then, yeah, okay. So for int row equals 0, row is less than rows, row plus plus. For every column, col is less than cols, col plus plus. So for every row, for every column, if this point is within the triangle, for every row, for every column on the entire damn screen because I lazy. So for every column on the screen, we're going to see if it's inside of the triangle. Okay. And so we will see if it is inside the triangle via cross product. Okay. So cross product. We didn't write one, did we? We have one in the other library. Whatever. We'll just do it ourselves. Or we can cross product 2 points. That might work. 2 line segments. That might work. Let's do. A point and a line segment. So we have a line segment, we have a point, and we want to see. Yeah, okay. That works. Yeah, let's write our own line segment cross product that takes a point. Why not? And we're going to return a double. I guess we're going to do scalar cross product. So we're going to do a cross product, and we're going to take a point const point reference p. So returns the cross product of start to end and start to p. So given start to end and p, it's going to cross product start to end and start to p. That's the ticket. Okay. So all right. So let's see. Int x1 is equal to n.x minus start.x, int y1 is equal to n.y minus start.y, int x2 is equal to p.x minus start.x, int y2 is equal to p.y minus start.y. Do you guys need me to sketch this out for you? So like, excuse me. So if you've got a line segment and you want to know if a point is on one side or the other, like you got a line segment, you got P, P's a point. You want to know if it's to the right or to the left. And so what you do is you draw a line. You have your line here, and then you draw a line to the P, and you just cross product those two. And so that's the 4 numbers. Does that make sense to you guys? So that's how far it is to the right, how far it is up for the first line segment, how far it is right, how far it is up on the other line segment. Okay. So now we're going to just return the cross product, and so we're just going to return x1 times y2 minus x2 times y1. Cool. Let's vertical space these out a little bit so it's a little bit more readable. And yeah, sure. Okay, so we've got that, and we got that. Okay, so for every point inside of the, every point, we're gonna have to mandate precondition points are held clockwise. So 0, 0, 10, 0. Zero, 10. So this is counterclockwise. So let's make it clockwise. So it goes. So it's going to go 0, 0. Wait, is that row first? Yeah, row 0, column 10. 0, 0 to 0, 10, 10, 0, 0, 0. Okay, yeah, it's clockwise. Or I could have adjusted the indexes. Okay, indices. All right, so for every point on the world, let's actually move it a little bit to the right. Let's add 10 to everything. And let's just verify that works first. A related function has no contextual type information. Really? No contextual type information. That sounds horrible. It's because of that, right? Okay. We don't have start and end anymore, so. Struct point has no member named x. It's row. Okay. X is column. Okay, column. Substitute row. Okay. Okay. There we go. So I moved everything down and right to the 10 pixels because I want to make sure that our system here is working for things above and left and right and down. So we're going to say for every point on the screen, we want to do a cross product with that between the line segment and that point. Okay, so double cross 1 is equal to the cross product of first dot cross product with the point P. And the point P, let's just make a point P. Point P is equal to a column. So we're going to cross product it with all of them, all 3 lines, and if all of them are either positive or negative, first, second, third, which one did we do first? I forget. I think if they're all negative, if any of them are negative, I think it's going to be outside, and if all of them are positive, it's inside. So, okay, so if cross 1 is less than 0, or cross 2 is less than 0, or cross 3 is less than 0, and we might have to flip this around just depending on what order I typed it in because I don't remember. If any of them are negative, then we are going to move the cursor to row and column. We can do that anyway, I guess. Move the cursor to the row and the column, and we are going to see out. I guess we'll set the background color. Set background color to be 0, 0, 0. And we'll set the foreground color to be white. Type would go a little faster. Okay, so we're going to set that. Okay, so if any of them are negative, we're just going to see out the minus sign to show that it's minus. Otherwise, we are going to see out a plus sign. And then this will tell us if we're doing it right. Ooh, look at that. Interesting. So I don't think this is correct, actually. So let's do that, and then do that after. Yeah. Okay. So maybe it's the other way around. Let's see. It's not a bug, it's a feature. So if it's plus, it might be we have the points in the wrong order. Plus, if the vertical one is facing the wrong way, it's supposed to be clockwise there, right? So 10, 10, 10, 10, row 10, column 20. Zero, 1. Okay. 10, 10, 10, 20, 20, 10, 10, 10. So that is clockwise. 0, 1, 2, that's correct. Maybe we're building these things improperly. Yes, that's fine. Okay, so it's A to B, B to C, then it needs to be C to A. Okay. Do you see that? I went A, B, and B, C, so that's actually going in both directions. It's bad. There we go. Cool. All right. So yes, everything worked according to plan. I just had the lines. I wanted to be symmetrical AB and AC, and I forgot that that's going to have them go in two different directions. So good. Worked right the first time, kind of. And it has a shadow. Yeah, the top left corner. It's interesting. Oh. Cool. All right. So now what we do is we are going to simply not draw any of those. Actually, we can just take that whole thing out. Huh? Have you guys ever seen that before? An empty command. That is perfectly valid C++. If any of them are negative, do nothing. Cool. Right. And then in that case, we don't need to do this whole rigmarole. Actually, this is a waste of time, isn't it? D2D, just put that up here. And we only need to actually print anything if we are inside of the triangle. Okay, so if we're inside of the triangle, we're going to move to the right spot and print a plus. And it should rasterize much quicker now, thank you. Because we were filling the whole screen with spaces, right? And yeah, so the color is going to be the relative values of the different cross products. Unfortunately, we're out of time for today, so we're going to have to pick this up tomorrow. But basically what you're going to do is you're going to add these three things up and set the red, the green, and the blue based on their relative proportions. And then you can have a very nicely done thing. On Monday, I think we'll pick it up with Z buffering and having multiple triangles with different amounts of depth and things like that on it. So that'll be fun. So I'll make a note here. To do, and Vim highlights that automatically. Use barycentric coordinates to color the triangle proper like. And the other thing I said was to do Z buffering, right? So So to do add depth. So it'll not just have screen coordinates, but it'll have a screen coordinate with a depth on it. And then we're going to be sort of in a 2D plus depth world where we can draw one triangle over another triangle. We're not doing any projections. That was the final project last year for my students. They had to do a projection matrix and all this other stuff. We're just doing screen coordinates, which is a lot easier. You don't have to project from the world onto the screen, or the screen onto the world. We're just using screen coordinates. Pretty easy. But we can have one triangle overlapping another triangle, and that's pretty cool too. Okay. So that is it for today, and work on your projects. You do have a project update due on Monday. I want to see screenshots from each of you guys on what you've done, and make sure you're on track for a next Friday finish. Okay, so I'll see you then. Peace out, you guys.